So today is the first lecture on number theory. Before starting our lecture, we have to know about what number theory actually is. Now, actually, number theory is the study of integers and fractions, that is rational numbers, how they factor and how they arise as solutions of equations. Initially, we will go through some basic definitions from divisibility and we will move slowly towards the theorems and definitions which is modern and important as per our syllabus. So initially we have to know what the actual definition of divisibility are. An integer b is said to be divisible by a, obviously a not equals to 0, if there exists some integer k such that b equals to ka, or here I mentioned that b equals to ma. That means if a and b are two integers, then the integer a divides the integer b if there exists m, which is also an integer, such that b equals to ma. We can easily denote it in the form of divides b, and if not, then the negation of this one is this. Then we have a new definition, which is arithmetic function. Any function whose domain is natural numbers is said to be an arithmetic function. That means if we have a function, defined a function from f such that natural to say complex, then this function is known as arithmetic function because we have the domain of natural numbers. That's why this function is known as arithmetic function. Then we have to suppose that for a given positive integer n, the number of positive divisors of n, obviously if n be an integer, okay, if n is a very a common integer, then the number of positive divisors is denoted as tau of n. This sign is called tau of n, and the sum of the positive divisors of n is obviously known as sum of n, not sum actually, it is the sigma of n. Then if we denote, suppose let us take an example, suppose 12. The divisors of 12 are 1, 2, 3, 4 and 12 itself. So into for the if we consider the integer 12, obviously positive integer 12, then we have 1, 2, 3, 4, 5. 12 have 5 divisors. Then if we consider the tau of n of 12, that means tau of 12 equals to 5, and similarly sigma of 12 will be the sum of all the possible positive divisors of 12, that is 12 plus 4 16, 16 plus 5 21 plus 1, that is 22. So if we move to our next slide, there are few examples that sigma tau of 1 equals to 1, tau of 2 equals to 2, tau of 3 equals to 2. Similarly, if you solve the following consecutively, then you will get the answers 1 2 2 3 2 4 2 4 of the all the taus of 1 2 3 4 5 6 7 8 9. Then if we denote the we know that tau of n is the number of positive divisors, that's why these are. Then there is an open example for us, that is 9. Then the divisors of 9 are 1, 3 and 9 itself. Then the tau of the 9 will be 139, that is 3. And similarly, if we go to our sigma function, that is sigma 9, sigma 9 will be the sum of 1, 3 and 9 consecutively. The sum of 1, 3 and 9 are is, that is 13. So if we go through all of our examples, whatever we did now, that is tau of 1 equals to 1, tau of 2 equals to 2, tau of 3 equals to 2, tau of 5 equals to 2, tau of 7 equals to 2, then obviously we'll got if we find the value of tau of 13, that also we have 2. Then by following our steps, we can easily say that if n is a prime number, but for the prime numbers, the value of the tau are always 2. And similarly for the sigma function, here it is sigma of 2 equals to 3, sigma of 5 equals to 6, sigma of 3 equals to 4, and sigma of 7 equals to 8. Similarly we can say for the sigma functions or the sigma, that for prime numbers the sigma values are always n plus 1. If n is a prime number, then the sigma function of that number will always n plus 1. So here is our remark, whatever I say now, that tau of 9 equals to tau of n equals to 3 if and only if n is a prime number, and sigma of n equals to n plus 1 if and only if n is a prime. So now this one is the summation expression of tau and sigma. So if we think that if summation d divides n f of d, this actually denotes, this term denotes the sum, the value of function d, as d runs over all the positive divisors of positive integer n. We already taken that n is a positive integer, that means n belongs to z plus. That means that the formula of the tau n in terms of summation d divides n f of d will be not actually summation d divides n, it will be 1, and similarly sigma n equals to summation d, where the sign summation indicates that we have to add together as many ones as there are positive divisors of n. Similarly, we have an example that's to find that tau of 10 and tau sigma of 10. We all in this process, that we all know by our earlier methods that 10 has only 4 divisors, that is 1, 2, 5 and 10 itself. That means if we denote that tau of 10 equals to summation of d divides 10 1, because because there are because 10 has 3 divisors, that means it will be 1 plus 1 plus 1 plus 1, that is 9. Similarly, if we try to get the answer of sigma 10, then we will by this process we will get 1 plus 2 plus 5 plus 10, which is 18. Now this slide is blank because we have to know about that fundamental theorem of arithmetic. From our very basic classes, we already know about the fundamental theorem of arithmetic, which says that for any integer, suppose for any integer n, it has an expression, it can be written in the form or in the form of the product of prime numbers. Suppose at first we can take an example so that we can understood easily. If we take the number 24, we can write it in the form of 1 into 2, 2 into 2 into 2 into 3, which is 1 into 2 cube into 3, or more precisely we can now I am intentionally writing this in the form of this. So now we can why should I wrote this in this form? Because we can write n in the form of p1 k1 dot p2 k2 following pr kr, where all of this p1 p2 p3 p4 dot pk pr, all of these are prime numbers, because for the integer n, obviously n is an integer, for the integer n, and in the integer n obviously represented in the form of the product of prime numbers. This is actually the fundamental theorem of arithmetic says. Now we have a theorem which says that for an integer n, obviously the product of prime numbers, that is the prime factorization of n, is the obviously n greater than 1, then the positive divisors of n are precisely those integer of d of the form of d equals to p1a1 p2a2 dot dot pr ar. Initially we will let me change the ink. Initially we will think for 1, because for the suppose 1 is a divisor, there if we denote the power for all the times that the power of the 1 will be 0, that is a1 a2 ar, all will be the 0. And secondly, if we say another way, that if we take any number, any integer, then every integer have two common divisors, that is 1 and the number itself. Obviously if we take the number n, if we take the integer n, then n also might be have obviously have two prime factors as common. One will be 1 and another will be n, because and n occurs when a1 equals to k1, a2 equals to k2 and ar equals to kr. Suppose d divides n, obviously by our first theorem that d, if d divides n, then it will be written in the form of n equals to d dot d prime, where d prime is an integer obviously, and both d and d dash are greater than 1. D equals to q1 q2 dot dot qs and d dash equals to t1 t2 dot dot tu, where qi and tj are primes. Obviously 1 2 3 dot dot s, that is represented in the form of qi and tj, both are primes, both are prime factorization of n. And if we followed by the next step, there it is written that d equals to q1 q2 dot dot qs, and which can be conversely written in the form of p1 a1 p2 a2 dot dot pr ar. Then here from this place our converse proof has been started, that is d equals to p1 a1 p2 a2 dot dot pr ar. So if we write it is in the form of n equals to p1 k1 p2 k2 dot pr kr, where we can easily wrote this in the form of p1 a1 p2 a2 and pr ar, that p1 k1 and this one both are here, it is the d, our d, and another one is our d prime. So we have both d and d prime, then we can write this in the form of n equals to d dot d dash, which says that d divides n. So we have our next theorem which says that if n equals to p1 k1 dot p2 k2 dot dot pr kr, what is this? Actually this is nothing but the prime factorization of n, which we says earlier also. Then we have to show that tau of n equals to k1 plus 1 k2 plus 1 dot dot kr plus 1. Initially we tried to solve the number, if we have any number, suppose 10, we can easily find the value of tau of 10 by finding its divisibility. And similarly we can find out its problems. Now if any number which is not counted easily, then we can follow we have to must follow this theorem to find out the value of that number. Now we have we have divisors of n equals to d equals to p1 a1 p2 a2 dot pr ar. Then our function tau according to the previous theorem, whatever we did earlier, the positive divisors of n are, here it is represented in the divisors form, which is d equals to p1 a1 p2 a2 dot pr ar. There are mostly k1 plus 1 possibilities for the exponent a1 and k2 plus 1, so that a2 kr plus 1 choices for ar. So we can easily write it is in the form of tau of n equals to, obviously it will be the k1 plus 1 k2 plus 1 dot kr plus 1 followed by that will be our asked proved. So now we'll solve. Earlier we solved the countable numbers, which or easy numbers dot whatever is smaller numbers actually, but now we have a comparatively greater number. That is this type of questions mostly come in many comparative exams, and in fact in net type exams or a national level examination also, that tau, if tau equals to 2024 2024, that means 2024, we have to found the tau value of this number. That is we have the prime factorization of this 2 cube into 11 into 23. It is the prime factorization of the tau. That means if we use the formula which I mentioned above, then by using the above theorem we can easily write this in the form of the power is 3 plus 1, that is k1 plus 1, k1 is the power, into what is the power of 11, that is 1 plus 1, and what is the power of 23, that is 1 plus 1. So if we write all together, that then we will have 4 into 2 into 2, which is nothing but 16. Now similarly we can easily find out the question, that is tau of 2023. If we find out the prime factorization of 2023 by fundamental theorem of arithmetic, then we will get that the prime factorization of 2023 is 7 into 17 into 17. Now 7 into 17 square, both are distinct. Then we will have 1 plus 1. If we find out the tau 2023, that is 1 plus 1 and 2 plus 1, which is nothing but 2 into 3 equals to 6. Similarly, you can try for the 360. Now we have a proof. We already find out the problem, which it says for something greater number, the tau. If there might be a question which says that there are how many numbers, how many divisible numbers of 2023, we can easily find out the divisible numbers of 2023 by this tau function process. Now we have another theorem which says that obviously there is an integer and the prime factorization form of n for all n greater than 0. Then we have to find the sigma. We have to prove that sigma n equals to p1 k1 plus 1 by p2 p1 minus 1 dot the product of p2 k2 plus 1 by p2 minus 1 dot pr kr plus 1 pr minus 1. So according to the previous theorem, whatever we did earlier, the positive divisors of n are precisely those integers d such that p1 a1 p2 a2 dot pr ar. To evaluate sigma n, we have to consider the product of both, that 1 plus p1 square dot p1 k1, which is nothing but that our divisor, and another one will be 1 plus p2 square plus p2 cube dot p2 k2, followed by PR number for PR. Then we can easily write that the sigma value of this number is P1 K1 plus 1 minus 1 and followed by PR KR plus 1 minus 1 by PR minus 1. Then we have an example which says that sigma of 2024, that means 2024, whatever we already found, tried to solve the value of tau of 2024 earlier. Now we have sigma 2024, that is 2024 equals to 2 cube into 11 into 23, which is 2 into 2 cube, that is the power of 3, k plus 1 minus 1 by 2 minus 1, and we have the answer 4320. Now we can easily find out the problems, which is for the 2023. This may be homework. And if we try the 180, the 180 equals to 2 square into 3 square into 5, that is sigma of 180 equals to 2 to the power 2 square plus 1 minus 1 by 2 minus 1 dot 3 square plus 1 minus 1 by 3 minus 1 and 1 plus 1 minus 1 by 5 minus 1. If we solve it, then we can have 7 into 26 by 2 into 24 by 4, that is 13 6, and if we find the product, that is 5 4 6. Now we have a question which come in NBHM examination. This type of questions might you can if you mostly you can have in various national level examinations. Here this is two easy questions as per NBHM pattern, that find the number. This type of questions gives you more marks. That find the number and easy to carry. Find the number of divisors of n where n equals to 2520. So in this question they asked find the number of divisors of n. Obviously, if they asked the number of divisors of n, what will be the answer? The answer will be the tau function. But there is a trick which they says that excluding unity and number itself. That means we have to find the tau value of 2520. There will get the number of divisors of 2520. Then we from the number of divisors we will exclude the value of unity and the number itself. So that will be tau of 2520. We have to find that. That is I am writing it directly. That is 2520, which have prime factorization of 2 cube by fundamental theorem of arithmetic, 3 square into 5 into 7. This is our prime factorization, but that means tau of 2520, that will be 3 plus 1, 2 plus 1, 1 plus 1, that is 4 into 3 into 2 into 2, that will be 48. Now there are 48 divisors of 2520. Now they asked us to exclude unity and number itself. Unity means 1 and number itself, that means we have to every number, in the divisor list, that number must be there. That means we have to reduce that. We have two numbers to reduce, that 48 minus 2, that is nothing but our 46. Thank you. Then in our next videos we will move forward for the multiplicative function, and we will solve many other examples related to this. You can also solve various examples provided by our elementary number theory books, and there are many reference books are there in the market. Thank you. We will meet in our next lecture again.